All right, here's another example of implicit differentiation from that WebAssign assignment. So number 8, something like your number 8. I'm going to go back to the beginning. Here's the whole worked out problem. If you want to freeze the screen right now, I figured you could just take a look at this and see the work. If that's of interest to you, check yours. Only thing that you might change down at the bottom is negative y squared minus 4y, the end result. You can mess around with the signs in there and make this look different, but I think this is probably as good as it gets. I'm going to go back to the beginning for the explanation. If that's of interest, hang out here and I'll go right to the beginning. Okay, so the first thing, here's the problem. That's an implicit form. I have not solved for y. Y is not by itself. And in this implicit form, the first thing we notice is there's actually two product rules on the left-hand side. Two functions multiplied together in xy squared, and two functions multiplied together in 4x and y that we can't separate. You have to keep them together to multiply, or to get the derivative. So what I have is that xy squared, that itself is a product rule. So I've set up the template for the two product rules here. The first one, underlined in red here, and then the bracket in red down there shows you I've got the steps for, derivative of the first times the second unchanged, plus the derivative of the second times the first unchanged. I set the parentheses for that. So, and then the green there is the second product rule, 4x and y. You have to know what the first and second functions are. You choose the first function. You can actually be somewhat flexible about that. In xy squared, there's no confusion what the first and second are. In 4xy, you could look at it a couple of ways, but we're just going to go with 4x is first, y is second. That means, let's go with the first one. In the xy squared, derivative of the first is 1, derivative of the second is 2y, but don't forget the dy dx when I put that in there. Then the second unchanged and the first unchanged in their spots respectively. This is the form of every product rule. I always start with the derivative of the first. You can actually start with the derivative of the second if you like. That doesn't matter. Order does not matter in the product rule. So then the other side follows a suit, so it's a similar process. Derivative of the first, 4 times the second unchanged y. Derivative of the second, when we're taking the derivative of y, is just 1 dy dx. In fact, you could skip the 1 and just call it dy dx times the first unchanged 4x. That is your derivative. Oh, forgot it's set equal to 0 because the derivative of 10 is equal to 0. After taking and doing this, you have to solve for dy dx. The process is isolating dy dx in a lot of these problems is subtract everything away until you have, or get the dy dx terms on one side by themselves. That means subtract away things that don't have a dy dx in them. And then you get dy dx by itself by doing some factoring. So first thing is I am going to take and first write this out, simplify a little bit. So I combined some things. 1y squared is just y squared. I switched around, put the x out front with the 2y, a couple other little things. Just take a quick look at this, pause if you need to. But I just combined a few terms and cleaned things up a little bit. Now I'm going to get the dy dx terms on the left and everything else on the right by just subtracting away the two things that don't have dy dx. So what I get then is this expression here equal to negative y squared minus 4y. Now I have to factor out on the left the dy dx terms out front. That leaves behind 2xy plus 4x, and then the right hand unchanged. And then we're going to divide away the 2xy plus 4x to get dy dx by itself. And the result is what we saw in the beginning. So there it is. That's your slope equation. That's the slope of a tangent line to this curve, which is not a function. So if you graphed it, this would not pass the vertical line test. You're going to get some waviness in there. It could be circular, could be all kinds of crazy things. But what happens is we can still find the slope of tangent lines at various places and get pretty excited about it. That was a pretty poor tangent line. I could do a better job than that. But the idea is that you can still find, and we still want to find, slopes of tangent lines to things that aren't functions. So this can be helpful. And do email with questions.